All right. Hello, everyone. I welcome you to this week's Tau seminar. It's really a pleasure to have here Jerry Harrington from Penn State University. Long time overdue. Jerry is a professor in meteorology at Penn State. He's also the endowed professor of the Wilson Faculty Fellow. For the grad students, maybe for after lunch, he's also the associate head of the graduate program at Penn State right now. So if you want to hear a little bit about advice, etc. I've known Jerry from his studies from the early 2000s. Jerry, I will say a few more words about him, of course, in a minute, but he does modeling, field, and experimental research. But I came in touch with his work modeling because he was one of the first and few saying in Arctic mixed phase cloud, how ice forms, there's maybe time plays a role. And he hinted very early to that. And I'm propagating that for 20 years and arguing with my community for 20 years. And so I was an early fan in principle of his modeling work. And now he turned and is a more experimentalist in recent years. And we'll talk about that today. So just to finish up here, he did his bachelor degree at the University of Iowa in physics, then got his PhD in atmospheric science in Colorado State University. He didn't go through a postdoc. He went promptly to a faculty position, University of Alaska in Fairbanks, was 3 years assistant professor there, and then came to Penn State, again as an assistant professor, got tenured, associate professor, full professor. Has been there ever since. He's also the editor of Journal of Atmospheric Sciences, where some of you, I'm sure, submit some papers, so maybe you get some inside info from him as well. And I'm not saying much more to that. I really welcome him. The title of his talk today, Ice Crystal Growth at Low Temperatures, Measurements, Theories, and Cloud Scale Impact. And please take it away, Jerry.
Thank you. It's nice to be here. I was in this area actually about 15 years ago, or maybe 20, back when DOE used to have meetings at BNL. So it's been a long time since I've been here. Before I get started, I'd like to thank some of my collaborators that I've listed in particular. So this work is done with a lot of people. Really, Gunnar Pakrivka and Dishwan Ray, my two graduate students who do experimental work, are instrumental. They've done all the measurements that I'm going to show you today. So I'm mostly showing you their work and some of the interpretations that we have for that. I've been involved in ice crystal growth problems for many years and worked on many different kinds of problems. I started as a numerical modeler and a numerical model developer. Many years ago, when I was at Colorado State as a graduate student, we worked on problems associated with rhyming, aggregation, and vapor growth, and have a number of papers in the literature on these different types of topics. Our work has been motivated mostly by my desire and my students' desire to understand basic physical processes in ice growth. And one of the things that really motivated us, especially early in my career, was trying to develop parameterizations for the growth processes of ice that actually better mimic the natural transitions that you see in real ice crystals in the atmosphere. One of our big motivations. Today, I'm going to talk mostly about vapor growth of ice, and particularly at low temperatures. So that'll be the top what I'll talk about today. So the motivation, I think, is relatively simple. We simply just do not know why ice crystals grow the way they do at temperatures, particularly below minus 40 degrees. Okay. I don't think that's an understatement. We lack measurements, specifically time series measurements. We do have measurements of growth rates, but we don't have time series. That's really critical. Without that timescale information, it's really difficult to say exactly how it is that you should model that growth. We don't know the critical supersaturations that you need in order to understand how it is that surface processes determine the growth rates. Okay, those haven't been measured at temperatures below minus 40 at all. And I'll explain what that is a little bit later on. John Nelson said this in 2005, and it's still true today. At low cirrus temperatures, the growth mechanism for ice is not even known. So there's a lot of things that we don't understand about the growth of ice, and one of the things that motivated our work is to try to improve this so that way we can actually evaluate and improve the methods that we use in numerical models. In order to motivate this a little further, I'm going to start off first and talk a little bit about what we commonly do in numerical models. And not only numerical models, it turns out this is also what we do when we sometimes interpret laboratory data. The most common model that we use for growing ice crystals from the vapor is called the capacitance model. And some of you may or may not have seen this before, but it's basically built into every microphysical scheme that exists. All right, it's universally used. This model does not have any mechanism to evolve the aspect ratio or the habit of a crystal. So when we look at crystals in the atmosphere, we see that they have all these different shapes. The capacitance framework that we use has no internal mechanism to change the shape. It actually keeps the aspect ratio constant. It's the way that's the way the theory works. In order to get any kind of shape evolution for a crystal, then you need to supplement the theory with something. Okay, so that way you can change the shape of that particle. Generally, the way we do this, and this is the way I did this as well when I was a graduate student, is we supply information from observations like in situ measurements that relate the mass to the size of particles. So that's one way that we do it. So we have to close the equation with some way to change the shape. One way to do that is to take an observation that you have from a cloud. Sometimes aspect ratio versus size relationships are used as well. So that way we can actually change the shape. All right. This is where the time scale becomes really critical, because from those observations that we have in situ, we don't have any time scale information. So we assume that the capacitance model gives us the right time scale for changing that shape. Okay? So the model itself doesn't have any way to change the shape. This can have consequences for our simulated clouds. Like, for example, one consequence that can happen in some numerical models is pulsing behavior. Sometimes we call this thresholding. What's shown here is a simulation of a mixed phase stratocumulus cloud, and this is the liquid water content in that cloud. So that's supercooled liquid water at about minus 15 degrees. And what you're seeing in these solid contours, that's ice precipitation that's falling out. And you can see it occurs in pulses, all right? This isn't actually realistic. It turns out that this occurs because we have no natural way to transition the shape in the capacitance model. So what we do, at least in this scheme, is we move small ice to snow. We do that by making sure that the mass is appropriately connected up so that way it's conserved. But what happens is that you very rapidly change the particle from one type to another, so its growth rate changes rapidly. This causes a really rapid increase in the growth rate, and you get precipitation of snow, but it occurs in these bursts. I chose this case to show you just because you can see that you get this very rapid transition that doesn't look very realistic. We also sometimes see this in orographic precipitation and in other fields as well. It doesn't always show up, but sometimes it does. And this is an example of a case where it does from a simulation that one of my students did. Okay, so the way we parameterize ice, it does have consequences with respect to the kinds of clouds that we simulate, and we might get things that are not so realistic. This is from a recently published paper on convectively generated cirrus, just to show you that the way you treat your ice crystals can actually have some major impacts on the simulations. What's shown here is the ice water content from the simulated, from observations as a function of temperature. They're shown as the black points. So those are your observed ice water contents in a convectively generated cirrus cloud. And what's shown in the two panels are simulations. One is with the Thomson scheme, which some of you may be familiar with if you deal with numerical models. It treats these crystals kind of like they're dendrites with an effective density because the particles are not spheres. They're kind of spread out and have arms. And that's shown as the shaded regions in here. That's the number density of the crystals produced. And in neither scheme do you capture the full distribution. You don't even get much of the shade. P3 is a scheme that treats the particles as if they're spherical, which is another treatment that people use very frequently, especially for cirrus. You just assume that the particles are spheres. And for cirrus, a lot of times they're just solid small spheres. And in this case, you can see that the ice water content is not very well predicted at all across temperature, all temperatures. The point that this particular article made is that if you have a scheme that actually allows the shape to evolve more naturally, and there's ways that this can be done, you get a much better prediction of the ice water content field. You can see from the shaded regions now that you pick up the pattern much better. And in particular, you capture high ice water contents at a little bit higher temperatures that are associated with cirrus clouds that were generated from liquid in situ. So picking up that evolution in the particle shape, it turns out produces a better overall estimate of the cloud fields. These are just some examples of what happens when if you're predicting ice contents in cirrus, and why shape and habit evolutions may be important. So some of the unknowns that we have, particularly with respect to the growth of ice crystals and the issues associated with modeling clouds, these motivate our work. In particular, there's a few things we're interested in. What's the primary ice growth mechanism at low temperatures when you get to below minus 40 degrees C? How is it that these crystals grow? All right, we would like to know fundamentally how that occurs. How well do our current theories capture that growth? Believe it or not, we haven't really done any comparisons because we've never had measurements, or very few measurements that we can look at. And then can we develop models and theories that improve upon what we've had in the past? Our group uses laboratory measurements, models, and in situ observations to try to do that. The goal is to improve what it is that we know about how ice crystals grow, and then use that to hopefully improve models. Okay, I'm going to start off first and talk about some measurements that we've done for small ice crystals grown at low temperatures. Everything I'm going to show you is for temperatures that are associated with cirrus clouds. So they're at temperatures below minus 40 degrees C. We can do higher temperatures in our laboratory, we just haven't done that yet. Where the data are the most sparse is at temperatures that are lower than minus 40. When you look at cirrus clouds, particularly very cold cirrus, they're composed of a lot of small ice crystals. We see that in the observations, okay? They're not very big. They can tend to be 10, 20, 30, 40, maybe 50 microns in radius. And a lot of times we'll assume that these particles are solid ice spheres. That's the assumption that we'll make. And a lot of people make that approximation. I've done that as well in the simulations that we do. So one question is, how good is this approximation? In order to look at the growth of smaller ice crystals like we have in cirrus, we've done measurements in what's called the levitation diffusion chamber, all right? And I'm not going to show you a picture of the chamber because it's a little bit hard to see what's going on there. Instead, I'm showing you this little schematic from my student, Alexander Harrison's paper in 2016. Our levitation diffusion chamber is a classic thermal diffusion chamber. We have a copper plate that's at a higher temperature, and there's a heat transfer fluid housing where cryogen goes in. This plate is cooled to temperatures that are maybe around minus 30, minus 40 degrees Celsius. And then we have a lower plate that is at a lower temperature. So because we have higher temperature and lower temperature, we have a static environment that's statically stable. And then thermal transport is from the top plate downward. Both plates are covered with ice. And so both are right at the equilibrium vapor pressure for ice. So water vapor then is sourced from the higher temperature plate, and it transports downward through diffusion to the plate below. We launch water droplets from a little launcher that's up here, and those droplets are charged. They get launched into the chamber. The bottom plate actually has a charge on it as well, and that provides a levitating charge that holds the particle up. Okay, so it's levitated electrodynamically. So that the particle doesn't slide left or right, we have quadrupoles that are up here in the top plate, and that stabilizes the particle so that way it sits right in the center of the chamber. So we launch a water droplet, the water droplet freezes, and then we can measure the growth by measuring the change in the voltage on the bottom plate.
You're doing one drop at a time?
One drop at a time, yeah, in this chamber. So it's only a single drop, and we grow that at different supersaturations, okay? Now, we can't grow very big particles this way. The radius of the particles are maybe 8 to 50 microns. So these are all smaller ice crystals. And we can do very precise mass determination this way, 2.5 to maybe 5% in terms of the mass. And this gives you an example of the kinds of growth rates that we can determine then from those laboratory measurements. I'm not going to show you the time series of mass that we get. Instead, I'm showing you the results this way, where we have the determined mass growth rate that we get from the growing crystal as a function of its mass divided by the initial mass, okay? So when the particle starts off growing, it has a ratio of mass to initial mass that's 1, and in this direction, it's getting bigger in time, okay? And unfortunately, you can't see my shaded region on there, which is too bad, showing the uncertainty range, but it's in there in the blue. These points are the data points. Those are the growth rates that we determine, okay? And what's shown by the black line is the growth rate you get from the capacitance model, assuming that you have a solid sphere. One thing that should be immediately apparent is that the growth rate of the crystal initially follows that of the solid sphere. And that's not too surprising. If you freeze a water droplet, it's a solid sphere, and it's going to start off growing as if it's a solid sphere. But you'll notice that once the mass reaches about 3 times its initial mass, you start to see a deviation in that growth rate, and the growth rate goes up and up and up and up and up. All right, there's a rise in the growth rate. What we think is going on here, so first of all, the growth rate is actually getting bigger, okay? It's not staying as that of a solid sphere like we'd normally determine or use in a numerical model. Instead, the growth rate is higher. We think what's happening is that right around this mass ratio, we're starting to develop branching arms on the crystal. Anytime you have a branch on a crystal that sticks out into the vapor, it turns out it drives the growth rate up. Now, that's something that we know. You can see it in measurements. The growth rate's going to rise. So we think there's a morphological transformation that's taking place right here. And you're starting to get branching small arms that are coming off, and they're causing the growth rate to go up. Okay. So kind of got that drawn on here as a little picture. Down here we have compact spheres, and then up here maybe something that might look like a rosette with some branching arms. And in fact, when we try to fit the data, if we use a model of a crystal that looks kind of like this, which is called a rosette, where you have arms that branch off, it turns out it represents the data pretty well. Now, we can't see the crystals in this chamber. They're too small. We can't image them, so we don't know for sure. So there's only circumstantial evidence at this stage that we might have small rosettes with these branching arms, with these increasing growth rates. Now, we see this over and over and over again in the chamber at higher supersaturations, that the growth rates are actually bigger. Okay? All of those experiments that we ran, and we've run hundreds of them, have all been done with pure water. And we always see at higher supersaturations that the growth rate tends to be amplified, probably by the fact that you've got arms that come off of those crystals. But water in the atmosphere is never pure. Okay, it's usually a solution. So or always a solution, actually. So another thing that we've done in the laboratory is we've launched small water droplets that are solution droplets and looked to see, does the solution make any kind of impact on the growth? Now, the reason we started doing this is because work that Bogdan and Molina had done from about 2010, or at least published from 2010 through 2018, what they showed is that when solutions freeze, you tend to get an ice core inside the solution droplet, and the solute gets expelled outwards. You end up with this concentrated solution layer that tends to surround the ice, and then the ice tends to penetrate through, okay, that solution layer, and then you get your crystal growing. And you can see that here in their experiments, that you get these little crystallites that come out from the solution as it freezes. So my students and I thought, boy, if that's happening, those little crystallites, when they stick out, they're going to grow fast, and that should change the growth rate. Do we see that in our measurements? If you freeze a solution droplet, do you get a different growth rate than if you froze pure water? Now, that's important because most experiments that we experimentalists run are pure water for reasons that are perhaps a little bit obvious. We want to control the system, right? So pure water is a good thing to go with. First, let me show you some evidence that we do see something different from pure water versus a solution. What I'm going to show you are 2 videos. The first one, and I'll start playing the one on the left first. Let me explain to you what you're seeing. This is an ice crystal that's been levitated in our chamber, okay? And let me start the video over. I'll go back and start it over. And I'm going to pause it. If we launch a water droplet into the chamber and we have a laser shining at it, it turns out we can produce what's called a diffraction pattern, all right? So these are light and dark interference patterns. From that interference pattern, it turns out we can actually get the radius of the particle, all right? This can be calculated using mean theory. This gives us size information. If I freeze a pure water droplet, what we see is these regular interference patterns, except what happens is the pattern slowly changes over time and morphs, and the interference patterns get a little bit wavy. And that's because facets are developing on the crystal. And so the pattern is changing from that of a pure sphere to something that's ice. Now, here's what happens if we freeze a solution droplet. Now, that pattern is a little bit more regular, and the reason it's a little more regular is because of the fact that this is a solution droplet. Now, it hasn't frozen yet. Okay, and this is at a temperature of about minus 50 degrees, by the way. Okay, that solution droplet is sitting there. Okay, and it's just levitating. Now, all of a sudden, bang. Did you see that? That was the point of freezing that you just saw. So let me pause this for a second. When the pure water droplet freezes, we don't see the scattering pattern changing right away. It changes slowly. With a solution, and it doesn't matter if the solution is high concentration or low concentration, this is what we see. Is it very, very quickly turns into something that is very speckled, indicating that the internal structure is now very complicated. Okay. So we see a very, very different freezing process, just like Bogdan and Molina were talking about in their work. So what do the growth rates look like then from this? Well, let's go on to the next slide. These are our measured growth rates. And I plotted this in a way that'll take just a second to explain. It turns out that we can fit the growth rates from the crystals very well with a power law. And I've got that equation written up here. Okay, dr/dt, r would be the radius of the particle. We're treating it as a sphere because it starts as a sphere. And it turns out you can write this approximately as the radius to a power p minus 1. Okay. It turns out for a sphere, this value of p is 0. Okay. The change in the radius with time of a sphere just goes as 1 over the radius. That's down here. That's this line here. Power law of 0, that's a solid sphere. On the x-axis is the mass of the crystal divided by its initial mass. So when it's getting bigger, it's going from 1 up towards something like 8. 8 was about as big as we could grow it in terms of the ratio of the mass. This power law exponent p up here is the best fit that we could get to the data. And we get pretty good fits doing this, okay? This line here shows what the p-value is, the power law, for pure water. The growth rate increases in this direction. It goes up and up and up and up, okay? So this is the point where we get the transition in a crystal from something compact to we think something that has arms that are coming off of it that causes the crystal growth rate to go up. And you can see that right here. The growth rate is rising. We're getting bigger and bigger growth rates. These are the values we get from Na solution, from a sodium chloride solution. We've also done this with ammonium sulfate, and we get similar results. Each one of these points is not a data point. These are many experiments, okay? So, and the bar that you see there is essentially your 95% confidence interval on all of the experiments. So this is a large number of experiments that you're seeing here, probably 100 or 150. Same thing for these experiments here. They all have very similar shapes. And what we see is that when we freeze a solution droplet, it turns out the growth rate is bigger, and it's always bigger, almost always, all right? And we think this is because when we freeze the solution, we're getting these smaller crystallites that are penetrating through the solution layer. We don't know for sure. We need to catch some of our crystals and take a look at them. And we're trying to do that, actually. It's not easy to do. Trying to get a crystal out of that levitation chamber and then putting it, say, under an electron microscope is not an easy thing. So, but it's something we're going to try to do over the next year so we can see, do we really see these tiny little crystallites that are coming out? But these growth rates are quite a bit bigger for those crystals, all right? They're substantially larger, and they're growing much faster. Okay, now, one of the things that we've done is we've taken these data and we've been able to put them actually into a numerical model. The way we do this is, if you think back to the slide I showed you earlier, The faster growing crystals out here, we think have these branching arms on them. We treat that like an effective density of the crystal. So when the crystal's a solid sphere, its density would be 920 kilograms per meter cubed, that of solid ice. But as it gets bigger, well, it's not all ice, right? It's got air regions. So you just reduce the density. This is something we do in numerical models, okay? If we say a crystal has a density of 200 kilograms per meter cubed, we don't mean that the density of ice is that low. We just mean that if you put a sphere around it, there's air and ice. That's all it means, okay? It turns out you can parameterize for a numerical model ice growth in that way. So a lower density crystal is simply growing faster, okay? So let me show you some simulation results, and these are the only model simulations I'm going to show you. This simulation is a simulation of mid-latitude cirrus. This was an observed case that we had in a field experiment. And this is what's called a large eddy simulation of the case. Now, if you don't know what a large eddy simulation is, don't worry about that. It's a simulation where you can actually resolve the scales of cloud motion, okay? You can get the updraft, downdraft structures and those sorts of things. We simulated this case with Morrison two-moment scheme. This is something that Hugh Morrison and I did. And for this cirrus, his scheme tends to produce these smaller compact ice crystals. The crystals are all small. And so if we look at the ice mixing ratio in a horizontal cross section for this cloud layer, we see something that has a very layered structure and it doesn't have much in the way of features. Okay. Now, if we do that, if we model that same cloud, but now include the fact that we can let our ice crystals develop these complex shapes with lower density and faster growth rates, this is what we get. Keep forgetting I can use this thing. We get that. Sorry for the differences in the color schemes. I forgot to remake the first image so that they were all on the same color scheme. This is the same cloud system, except simulated with crystal densities that match our laboratory observations. And now what happens is we get cirrus uncinus instead of the layered clouds. What you're seeing here in the contoured regions, this is the ice water content, so it's your ice water mass. It's very high here because this is what's called the cirrus generating head. That's a cell. If I were to plot the vertical motion, you would see an updraft here, okay? And then what's shaded is the ice effective density, okay? The light shades are low densities. So these are crystals that should have these branching arms, and they should have faster growth rates. And you see these fall streaks associated with those lower density crystals. They're a bit bigger and they're growing faster, so they tend to fall out, okay? They fall out in these streaks. The higher, the darker shades, these are higher density crystals, more compact, okay? We tend to have these concentrated in regions where there's lower supersaturation. They're just not growing as fast, and so they're much more compact. The lower density crystals tend to be concentrated in regions where the supersaturations are higher, so the crystals are growing rapidly, and you're developing these arms or these effective densities. So pretty big differences depending on whether or not you treat those small particles as if they're solid spheres, or if you treat them as something that could develop an arm and then a faster growth rate. Okay. So it can have some pretty substantial difference. And by the way, there's no aggregation in this simulation, nothing at all. In fact, I had it turned on, it didn't do anything. These are all just purely vapor-grown crystals. Okay, so those are all associated with smaller crystals. We're also interested in bigger crystals, okay? The kinds of crystals that you sometimes see when you look at snowflakes and so on and so forth. Growing larger crystals, we can't do that in our levitation chamber. The reason we can't is because eventually the particle falls out. It just doesn't have enough charge on it. So it'll sediment out after it gets to about maybe 50 or 60 micrometers and fall to the bottom of the chamber. If we want to look at bigger crystals, we have to have another way to do that. So we've developed recently a new chamber where we have a similar design, where we have a higher temperature plate up here, and there's coolant flow that comes in. The bottom plate is a lower temperature. So again, we've got a statically stable environment. There's ice coating both plates, top and bottom, okay? So the water vapor source is from the top downward, okay? So we can produce any supersaturation we want in this chamber, same as the other chamber, just by changing the plate temperatures. We can go from low temperatures, low supersaturations to high supersaturations. We can go as high as we want. We can go to 200% liquid saturation if we want. We've done it, actually. It's amazing the crystals you see at 200% water saturation. They become nuts. I should have brought some videos, but my grad student was like, no, don't show them. Because they're not realistic. We don't see 200% relative humidity in the atmosphere with respect to liquid. We bring in support in through the side, and then there's a glass fiber here, and then we try to nucleate the crystals right at the end of the glass fiber, okay? The reason we came up with this design is because we were trying to mitigate some of the vapor competition that people had in prior designs. So there used to be designs where you would have a substrate going vertically from the bottom to the top, but the problem is you get crystals then that grow everywhere on the substrate. So now you have competition among the individual crystals above you where the vapor source is. Now it's really hard to trust the growth rate that you're getting from the crystals along the substrate. By bringing it in through the side, we have nothing above. The vapor source is from above, right? So then what that does is it means that we have nothing in between that then is affecting the crystals. We also have a bottom entry that I don't show here, which we're going to try, but it's a little harder to do. Bringing a substrate up from the bottom, so that way there's then nothing in the way of the growing crystal. We have orthogonal telemicroscopes on this thing, okay, that can give us a resolution to about 0.4 microns, which is nice. And the reason we have it set up orthogonally is because then with rotations, we can actually get the dimensions very accurately, okay? The rotations don't work super well yet, but we're working on that. It works pretty good, but not great. We have other things we need to do there. There's a limitation here, which is we can't yet test out ventilation. When you get to bigger crystal sizes, as they fall, that falling motion will ventilate them. And the reason I put yet here is because we're doing that next. So ventilation is one of the things we're going to look at next. Okay, and this is all due to my student, Gwenor Pakrivka. She's got a manuscript that's she's just about ready to submit it. I haven't looked at the recent version yet. So I'm showing you some stuff we haven't submitted yet to the journals. Again, these are all low temperatures, -40 to -70 degrees is what we're running. So these are some examples of the crystals that we grow. This is one case that she ran at -50 degrees and the ice supersaturation was 54%. So this is a pretty high supersaturation. You're getting up to near liquid equilibrium, right up to liquid saturation, okay? We've grown crystals at various supersaturations, not just high ones. The high ones are kind of nice to look at. The substrate is right here. Okay, that's the very end of the substrate, and you can see that you have a column crystal growing off this end here. You can actually see the hollowing on the crystal. If you look right here, that's the hollowing that occurs inside that crystal. All right, it's hollowed. This shows the growth from 1 hour to 1.5 hours and 3 hours. Okay, you can see the crystals getting bigger and bigger and bigger and bigger as it grows in that supersaturated environment. This is from our second camera. It's a little bit of a better image. I should have made this a little bigger for you to see, but now you can really see the structure in that column crystal. Okay, and you can see this other one that's kind of tilted off to the side. You can see that the crystal is hollowed. If you look at the very top, you can see that there's just a rim here associated with what we call the basal face. And that's the remaining part of the basal rim. And inside, you can see that it's hollowed downward. And we can measure that hollowed rim. How are we doing on time? We're doing great. So here's the measurements that we do. What we do is we're able to get what we call the C length of the crystal, which is this dimension. It's really 2 times the C length. Okay, that's the major dimension of the crystal. We can usually get that to within 10 to 15 pixels. So that means, you know, an error of maybe about 5 to 10 micrometers. Okay, so we'd like to get that down a little bit lower, but that's the case right now. And this is the A dimension of the crystal, okay? And we get that from both cameras, and then with a rotation, we can actually get the lengths pretty accurately. Another nice thing about the device is that in rotation, sometimes you can see the remaining part of the basal face, which you can see right here. You might have to look pretty carefully. But what I have with the arrows here is just showing that rim of the basal face that's remaining. And the reason why that's important is because that's where the vapor is attaching, is it attaches to that part of the basal face. There's not much that's going in interior to that crystal. Okay, let me show you what the growth rates look like. Here's what we get. So those are the measurements. This is what we call the semi-length. That's just half the dimension up the prism face, which is the C dimension. I should have drawn that as just halfway up, but I didn't. And then the A dimension is across the hexagonal face. That's a planar crystal. You'd have to extend it downward to make it into a column. Okay. But that's just to show you what the dimensions are that we plotted here. This is that C length. That's the measurement. Okay. And this is the error bar. And then this is the basal face length. And then this green region is the hollowing width. So if I go back to my prior image, it's how wide that part of the basal face is. That information is important because that's where the molecules are attaching. If you want to calculate the growth rate, you need to know what that is. So one thing that's interesting is you can see that the C dimension growth rate becomes pretty linear after time. And that's something that we expect from crystal growth theory is that rate actually will just increase relatively linearly. You can't see this for the A dimension because I should have plotted it on a log scale and then you would see it. Now we have our time scale information. This is what I've been after, Daniel. I want that time scale information. That's really helpful for me to interrogate my numerical models and my theories. Okay, I want to know what that is. By the way, the hollowing width, you can't really see it, but it's about 10 micrometers. And it doesn't change a whole lot, which I found interesting. Okay, so what we would like to do is we'd like to model those crystals and be able to say something about them. Right away, you might realize that I can't really use the capacitance model because I have no way to change the aspect ratio of the crystal, but here clearly the aspect ratio changes. So we have a model that actually allows us to include surface processes that control the shape evolution. And I've got a little bit of an image of that here from a paper that Wood wrote in 2001. Our model works pretty similarly. We have two kinds of ways that the crystal can grow. One is by something called spiral dislocations, and that's shown here. In the center of this face, what he's doing is he's modeling what's called a dislocation. When your ice crystal, when you form ice and it freezes, there's an awful lot of breaks that occur. And that can lead to little dislocations in the surface. And then those wrap up as spiral ledges, and the molecules actually attach to those ledges, and that's how the face grows. So the face will grow by these ledges propagating outward. That's one mechanism. This mechanism is very efficient growth mechanism for ice. Another mechanism is called step nucleation, where you nucleate the steps near corners and edges. Okay, and then that produces the steps, and then they propagate across. All right. Theoretically, it turns out you can calculate the growth both ways. To do that, you need what's called a critical supersaturation, and that's something that we've never had at temperatures below -40. The critical supersaturation tells you when you're going to start propagating those ledges across, and it tells you how fast that they're going to move. So it's a measured quantity. Our crystals don't look like this. They look a little bit more like that. They're hollow internally, and they have this hollowed width. That's the growth region. Okay, now I can measure that. So we have growth that occurs only on this region around here. Okay. And we have to make an assumption about where our steps originate. Do they originate in the centers of the faces? Do they originate near the edges? We made a choice to have the steps all originate right near the corners. Okay, and there's a reason why we did that. John Nelson in 1996 and F.C. Frank in 1982 had hypothesized that it's steps generated near the edges that is how you actually get atmospheric crystals. All right. But we've never been able to test this at temperatures below -40 degrees because we've never had any measurements, right, to do it. All right, so we went forward with this theory to see, does this explain our measurements? Okay, so here's the fits. The solid line here, and this is to the growth data I just showed you. This is assuming that you have steps forming right near the edge of the crystal. So this is that C dimension growth, and this is the A dimension growth. It turns out we can get really good fits to the data. And this is true for every single case that we've run, and we've run a lot of cases inside this chamber. Now I'm showing you only columns. We also have planar crystals, but columns, it turns out, are a little easier to analyze. That's why we started there. Start with the easy thing, then go to the hard thing later on in life, right? So we started with the simplest stuff. We were able to fit this with critical supersaturations, and we did pretty well. We get 8% and 10% for the basal and prism faces, respectively. If you don't know quite what that means, don't worry about it. This is pretty close to some estimates that people had done for what the critical supersaturation should be on those faces. So the model seems to work pretty well in terms of reproducing the data. Now, what are the other lines that I have on here for you? Well, this is the capacitance model, the dashed line with the points, okay? It turns out for the C dimension, if you use the capacitance theory, remember the aspect ratio can't change here. So we just fixed it as a constant, which is what you have to do if you don't know what it is. It doesn't do too badly at picking up how fast the prism length is increasing. It does horribly for the A dimension. And the reason why is because it has no mechanism to slow down the growth on that A dimension. That A dimension is growing very slowly because steps aren't forming. But in the capacitance theory that we use in all our numerical models, there's no way to slow that growth. So it's always going to be there. So the capacitance growth is too big. If I actually take the capacitance model and do what I often do in numerical models, which is I force it to have the aspect ratio that's measured, now it gets worse, actually. The C dimension now grows way too fast, although the A dimension is a teeny bit better, but not much. So if I force the capacitance model with my observations, I get something that also doesn't match the data. So far, I haven't found any way that I can match the capacitance model to the measurements. And the reason why is simply because that A dimension doesn't change much, and there's no way for me to treat that in a capacitance model. Okay, I have a couple more things I want to show you. Now, this is just one experiment, and we've run a lot of experiments. And what I've shown is that if I grow crystals by assuming that the steps form near the edges, I can model the crystals pretty well. So we're now getting to the point where I think we can answer John Nelson's question. What's the primary growth mode for crystals at low temperatures? Well, this is suggesting it might be steps forming near the edges, and that it's the nucleation of the edges that are the nucleation of those steps that are important. One of the things that comes out from edge growth theory is that if you take the growth rate of this dimension, the C dimension, and ratio it to the A dimension, over time, it should actually asymptotically approach the aspect ratio. That's a prediction that comes from the theory. Theory predicts that. So the ratio of those two growth rates should become the aspect ratio over time. I could show you time series from our lab measurements, and that happens in almost all our cases, every single one. But instead, what I'll show you is this. This shows all our measurements, okay, that we have so far of all column crystals at temperatures between about -45 to about -65, or I guess -50 to -65. This shows the ratio of those two growth rates, C dimension to A dimension. That's shown on the y-axis. And on the x-axis is the aspect ratio. We take an average because it fluctuates a little bit. The fluctuations are shown by the error bars, actually. So that shows you the variance that you had. These are all our measurements. That's pretty regular dependence. In fact, Daniel, when I saw this, I was thrilled, right? From a measurement, this is nice, okay? Numerical models, you get perfection. For measurements, you never get something that looks that good. The dashed line here is the prediction from edge growth, assuming that steps nucleate near the edges. The green line is a regression line through the data points with an R-squared value of 0.93, and the slope is exactly 1. Okay, that's about as good as I could imagine. This is suggesting that for all of our columns, Yeah, and when Glennar showed this to me, I was jumping out of my seat. Like, my God, I can't believe it. It seems like these crystals are growing by steps nucleated near the edges. And this is showing that what John suggested in 1996 probably is the case even at lower temperatures. Let me show you capacitance theory. That's what you get from capacitance theory. Okay, it's way too low. And the reason why, of course, is because of the fact that you don't have any way to change the aspect ratio. Some people in the audience, maybe nobody, but some people may be aware that Dennis Lamb and J.P. Chen had a theory in the 90s for changing the aspect ratios of crystals. It's called adaptive habit. I've built actually a cloud model based on it. So has J.P. Chen himself. So have a number of other people. This allows the aspect ratio to change naturally. Okay. This is what that theory predicts. It predicts aspect ratio changes that are way too fast. So that theory doesn't match either. Okay. What we've been working on with my graduate students is we have a way where we can take this theory and get it to come down here. So that way we can use it in cloud models. My student's working on the publication. Maybe you can hurry him up as he moves through. So with the last few minutes that I have left in the talk, so these are what our measurements are. I'm really excited about the substrate measurements. They're working better than I actually had hoped that they would. They're telling us some things about crystal growth at temperatures below -40 that we've never seen before. And so this is really useful to me just from the perspective of trying to understand ice crystal growth, but also from the perspective of trying to develop numerical models. One thing that I started asking myself is how well do our laboratory measurements compare to in situ observations? All right. You take measurements in cirrus, and then you take a measurement in a laboratory. You know, how well do they correspond to one another? From an observation in a cirrus cloud, I have no growth measurement, right? There's no way for me to tie a time scale to what I get from an in situ observation, but I can get a time scale from a laboratory measurement. We ran a field experiment at the Southern Great Plains site for DOE a few years ago, where we used an in situ sampler on a balloon. We captured crystals in cryogen, brought them back to the surface, put them in liquid nitrogen, and then we can interrogate them under an electron microscope. The reason we did this is because we wanted to look at the detailed structures of those cirrus crystals and what do they really look like? What are their structures? Here's some examples of what you see in those mid-latitude cirrus. Okay, here's a bullet rosette with a triangular face. Look at how hollow that thing is. It's incredibly hollow. Okay. Here's a crystal with actually it's cubic symmetry. That's really a cubic crystal. But again, you see these hollowing. This is called a twinned column, where you have two columns that are inserted into each other. Again, very hollow. Okay. This is a very complicated polycrystal, where you have faces in all different directions. And this is a really, really tiny column. This is 20 micrometers, and you can see that hollowed width in the hollowing that occurs inward on that crystal. We have tons and tons of these from the field experiment, and we painstakingly measured the dimensions, okay, of the column crystals. I'm just going to show you, I'm going to show you columns and plates, but I'm going to focus on the columns because that's what I've measured in the laboratory. And the basal faces, and then how wide the hollowing region is. So we did all of that. Here's what the measurements look like from in situ. The crystal dimension is on this axis, and this is really literally how long the crystal is. This is the major length shown here. These are scatter points, okay? And these are all columnar. The planar ones are down here. You can't see them, of course, because they have aspect ratios, which are less than 1. All the bigger aspect ratios are your column crystals. They're the ones where C is bigger than A. In order to get a really nice long column with a big aspect ratio, generally the minor length of the crystal is less than 20 microns. So you have a very thin basal face, but a much longer prism face. Well, that makes physical sense. Crystals with aspect ratios near 1 are compact, and so both dimensions tend to be fairly similar. And they also tend to be fairly small. Let me put the laboratory measurements on here for you. There they are. I'm really happy about this too. Now, for the laboratory measurements, I got to be careful because I grow these crystals. Well, I don't do anything anymore. My student did this. I mostly fill out reports. Now that's not true, but actually sometimes it feels like that. Everybody older's laughing because you know what I'm talking about. Yeah, I fill out a lot of reports, but I do some science still in my life. But this is really stuff that Gwenor has done. I had to actually pick a time scale because she grows these crystals for 8 hours. So we picked about a half hour to an hour, which we thought would be a typical time scale. And the green points are the major lengths of the crystals we grow in the lab. And then the red points are the minor dimension, the smaller dimension. And it's amazing how well they line up. You know, the crystals we're growing in the laboratory have very similar characteristics to the ones that we actually see in situ. And that actually includes the hollowing width. Yes?
The bigger crystals that you grow in your lab, you grow them with pure water or solution? It
Uh,
doesn't matter.
the jury's out on that. Okay, we've tried solutions and we see no difference, but we're going to try something different. Because, well, yeah, actually, so I don't know how to answer your question yet. Everything's pure water for now. We've tried solutions, but it hasn't been such a success so far. It's actually a tough measurement to do. It's a tough way to get the crystals to form on the substrate. So the jury's out on that. These are all pure water. Okay. Even the hollowing width, if I showed you that image, you would see that it's actually very similar to what we see from the in situ observations. So we're very happy with the fact that what we're seeing is also pretty similar to the things that we measured in ice ball. There's some caveats. From our ice ball measurements, everything's a projection. Okay, so these lengths are going to be smaller than the actual lengths from the in situ crystals. They're actually probably a bit bigger, but we have no way to deal with changing the projection length to an actual length in most cases. But at least for a qualitative comparison, it's nice. It also provides some strong indications that perhaps the laboratory measured growth rates now are similar to the kinds of things you might see in the real cloud because they have similar structure. And that's the end of my talk. Here's some take-home messages for you. Small crystals deviate from capacitance, and we think it's due to transformations into complex crystals. The deviation seems to be largest for crystals that are formed from solutions. We hypothesize that this is because you get, like Bogdan and Molina showed, thinner arms that stick out of the solutions, and then these things grow faster. We don't know for sure, but that's our hypothesis. Power law parameterizations of this seem to produce realistic looking ice densities in simulations of cirrus. Columnar ice crystals growing at temperatures below -40 seem to be growing by steps nucleated near their edges. Okay, so we think we now have a handle on what the growth mechanism is. I say this is a tentative conclusion because we still have a lot of work to do. One thing that I think is really interesting is that the crystals that are growing in our chamber are certainly very complex. They have faces that are not flat facets, okay? And yet what's interesting about it is that they show indications of kinetic limitations even because of that complexity. Capacitance theory, we can't actually reproduce the measurements even if we use the measured aspect ratios. And we're happy with the fact that our measurements seem to match what we see in situ. And that's it. Thank you. It's been a couple minutes too long. Sorry about that, Daniel.
No, great talk. We have 5 minutes for questions before we head to lunch. Chef, please.
Jerry, great talk and congratulations on having a life that allows for occasional science. Really cool.
Yeah, we can talk about that later.
I have a ton of questions, but I'll try to make it 2 or less. So the real world, even in the Arctic, can be really dirty.
Yeah.
Like if the Arctic atmosphere has a biomass burning plume. So as I recall from some of the literature, if you grow crystals in the presence of water-soluble gases, like formaldehyde is an example, you can change the rates of growth on the basal.
That's right.
Prism planes, meaning the aspect ratio. And so, yeah, it's going to be 2 questions. Have you ever tried doing that to see if soluble gases have any impact? If the answer were yes, that that thought makes the idea of taking crystals out and doing microscopy with them a horror story, because you can't change the gas phase environment, not just the supersaturation, but anything else you might have in your laboratory air. I mean, it's just one of the hardest things you can ever do.
Yeah.
Anyway, there's two questions in there.
No. I know exactly what you're saying. So I've been chatting with Bill Brune about this actually, because we would like to, everything that we're doing is a pure water vapor. Now, the reason why, of course, is that first I want to start with something that's as controlled as possible, right? Pure water vapor. You know, even the seals that we use for the chamber are things with very low vapor pressure so that we can assure that there's no degassing. You know, we're trying to be very, very careful about that. Then the next phase would be what happens if you introduce a gas? Does that end up changing the crystal and the crystal structure? So that's something we do want to look into, but we haven't done it yet.
Yeah, it's been done, but often, including by me, with really dirty air
Yeah,
that probably isn't too relevant to the real atmosphere. But
Yeah.
but it is interesting.
it is interesting.
It doesn't take much to impact the surface structure, right?
Yeah, one thing that I found was interesting about these experiments that I didn't show you is that once that crystal shape and structure gets set in, it's actually pretty hard to change it. So because our chamber is so shallow, it turns out that we can change the supersaturation very quickly. This is nice. It allows us to do supersaturation change and also change T. So we've done this where we change the temperature and we move the crystal from -50 to -30, -20, and even -15. And it will stay columnar. Okay, and the hollowing width might change a bit. But we really have to jack up the supersaturation to water saturation or above, and then we start to see a change in the shape and the structure of the crystal. So part of me wonders what's going to happen when we introduce a gas, right, in terms of the aspect ratio evolution, a foreign gas that's not water vapor. You know, my hypothesis would be if the crystal structure is already set, it may not do much. But if you're at the phase where you're developing that aspect ratio, it may do a lot. So then maybe after the period of nucleation, you would see some substantial changes. I'd like to do that problem. So this is in my mind, in addition to, we're developing a new chamber where we can do ventilated growth, but this would then be a chamber where I can introduce a gas much more easily. The diffusion chamber is hard to do, right? Because you got that low temperature, how are you going to introduce flow? And you can't really introduce flow into it. So you'd have to put the gas in initially. And then what's going to happen to it over time in that diffusion environment? But if I've got an environment where I've got a flow that I'm continually cycling, now I actually can introduce a different gas. And I can look at your problem. Great question.
One thing at a time.
One thing at a time in my busy life.
Anyone? Josie, please.
So I was thinking about your field campaign and all, and just wondering, what if you, instead of having salt, you had some organic compound?
Yeah. I don't know the answer to your question, but that's another thing we've been thinking about is actually using organics. You know, in fact, I've been working with, so Miriam Friedman, I don't know if you know her, she's in our chemistry department. She's one of the ones that I'm working with on this, is what happens when you introduce organics, because I have no idea how to do it. But she does. And so yeah, that's a problem that we're planning on looking at next year.
Okay, well, Daniel and I do organics.
I know, we've talked about that. Great question.
Anything else? Maybe have a quick comment and then we go for lunch. Yeah, with the gases, I mean, it comes back to polar stratospheric clouds. There are many studies, NO2, nitric acid, and other compounds, and the adsorption and interaction with ice phases, because folks had to figure that out due to the reactivation of this chlorine species. And there are some studies on that could help.
Yeah, right.
That's one thing. I just want to mention, especially for the foundation students, or this crystal growth is really important. You mentioned the ice water content, or it's not right in our models. But for radiative transfer,
Yeah, I didn't mention that.
Manfred Wendisch, the executive editor from BAMS, has really nice studies. They fly with a plane over a cirrus.
Mhm.
They model the up or below downwelling, and depending on the shape of the crystals, they get hundreds of watts per square meter different results. We're talking about 2 watts per square meter, hundreds of watts, depending rosets, depending
Yeah,
columns, etc. And it's a really important issue.
yeah,
And I bet most of you would have not thought that the crystals are hollow. I mean, even I'm doing it for 20 years, and I'm always astonished that they're hollow,
yeah.
which is a kind of a mind-boggling thing.
Yeah, most of the ones we see are hollow, even
yeah.
the smallest ones.
And if you go, of course, to higher temperature clouds, mixed phase clouds, they grow differently. If they grow faster, even at -20, it affects the precipitation, the hydrological cycle over the continents. So it is, I mean, it looks very specific topic, but it will affect all our models and radiative transfer, climate, hydrological cycle, convection.
Yep.
Yeah. So it's very fundamental. And indeed, we don't have any of this data. This topic has not been really studied the last 20, 30 years. So it's really fun to see that someone from modeling starts doing the experiments, and I'm an experimentalist and become a modeler. So we are the opposite. And with that, I stop. We can talk more at lunch. Everyone is welcome. And thank you all. And thank you, Jeff.
Oh,
Great job.
thank you.